Hello students, this is the recording for the 5A notes on elements. So taking a look, please make sure that you have watched this week's announcement video. Today is May 8th and we are on day 18 out of 45, so it's going by really fast. Today we are working on elements and the 5A notes. Remember that Fridays are only support, so if you need help on labs or exams, please come to support today at 2 o'clock. Some quick announcements in addition to what's already in your announcements video. Please remember that the 4E exam was due yesterday. It's being zeroed out today. It is all multiple choice, and we did provide all the class recordings next to their related questions. Everything was covered in class, so if you get stuck at any point, watch the associated class recording, and that should help you do really well. Remember, it's impossible to pass without the labs, exams, and STAR 360. If you see here in red, that is worth an entire 75% of your grade, so it's a huge part of your grade. It's impossible to pass without it. Even if you do all the notes in our course, you still would not have higher than 25%, which means you would not pass. So you have to do other things besides the notes. Please keep in mind that the Q3 extension that occurred due to the closure, the soft closure, is now ending. It's ending today at midnight. So if you are not passing any of your Q3 courses after midnight, please be aware that you will receive an F on your report card. It's a little bit different from this quarter. This quarter, we're not really doing Fs, but for Q3, there will still be Fs. So please make sure that you actually get your Q3 courses up to passing. All right, so we are starting a new unit. We're going to be working on Unit 5, Elements. We'll talk about elements, where they are on the periodic table. You can see a snapshot of part of our periodic table over here, explain why an element is placed where it is in the table, and conclusions you can make about the element based on its location. We'll also talk about some differences between metals and nonmetals, and we will begin to talk about compounds, which will be really important going forward in our course. So today we should be able to identify the properties of elements, describe the theory of the atom, identify characteristics of an element by using the periodic table. So the periodic table is a tool that we want to be able to learn how to use it today, and explain how fusion, something we already learned about, is able to create elements. So a lot of this is continuing from Unit 4. Keep in mind that this is chemistry, so we will be using this as the basis for the rest of the quarter, and a lot of this stuff will be kind of spiraled into everything that we're learning. Today you should be able to complete the 5A notes with an 80% or higher. Please note that I said 80% or higher and not necessarily 100%. You do have to pay attention, you do have to work hard today, because you will have an exit ticket where I don't give you the answer. So the exit ticket is worth 20% of your 5A notes. So if you don't get that right because you're not paying attention or you're not following along, then you won't be able to get 100%. So make sure you're following along so that you do really well on your exit ticket. And here's the rest of our agenda over here. So at this point, sorry, ignore this, we're not in live class. At this point, please open up your notes. You can go to your grades tab, you can go to the class plan or the like events underneath your class plan on your course page on that left-hand menu. So it's all there, it's easy to find. Otherwise, you can go to Content, Unit 5, scroll down, find the 5A notes, and then click Start. Again, answers are going to be provided word for word throughout the lesson. The only exception is the exit ticket that you need to be able to do on your own based on what you learn in this lesson. So make sure that you are learning. Keep yourself accountable to that. All right, so our quick mind map for today is that an element is based on the number of protons. We've learned about protons. We'll review those today. And it is the basic chemical unit of all matter. So first off, we should be able to define figure out which of these best defines an element. So go ahead, I'm going to read these off, take a moment, pause the video, figure out what you think the answer is, and then continue playing and we'll kind of review this. So A, everything in the entire universe that has mass and volume. B, a single smallest unit of matter that keeps its identity. C, a pure substance made up of several of the same atoms. Or D, two or more different atoms bonded together. Go ahead, pause the video, think about what you think is the best definition of an element based on what you learned in units 1 through 4, and then continue playing. All right, so if you take a look here, the correct answer should actually be, it is a pure substance made up of several of the same atoms. The rest of these are also definitions that are related to this idea of matter, but let's go ahead and talk a little bit about those different nuances of how they're a little bit different from each other. So let me go ahead and clear this and keep on moving here. All right, so taking a look here, one of these, everything in the universe that has mass and volume, that's just going to be matter in general. So everything in the universe that has mass and volume volume. That one's actually just the overall kind of big picture, just matter. Everything's made up of matter. Now, a single smallest unit of matter that keeps its identity is going to be the atom. Remember, a single piece of matter that keeps its identity, that is just a single atom. On the other hand, if you take many of the same atoms and you put them together, that's going to be your element. So for example, you can have an atom of silver, but you can have many atoms of silver, which is the element silver. Okay, so this right here is a pure substance made up of several of the same atoms. And then taking a look, a compound is something else that we've already learned about. That's when we actually get different atoms, and those different atoms start to bond together. All right, so that's going to be a compound. This is going to be number 1 in your notes. Make sure you pause the video, fill this in, and then continue playing when you're ready. All right, so moving on, we're going to go ahead and dig a little bit deeper into talking about elements. So remember, element is a pure chemical substance, and you cannot break it down physically or chemically into anything simpler or into anything different. So for example, we have gold. This is a gold atom. If you have many of the same type of gold atoms, that is the element gold. So elements are made up of several of a single type of atom. You can see over here a pure gold bar. And if you were to try to break this down physically by dividing it in half, you would still just end up with the same gold. And even if you were to try to break this down through a chemical reaction, it wouldn't be possible. Gold is as simple as you can get. You can't break it down into anything that's not gold unless you start messing around with the nucleus, but that's not a physical or chemical change. That would be a nuclear change, and that would require nuclear reactions, which would change the identity. So an element, though, is a pure chemical substance made up of atoms that keep their identity. And our example is gold. So you can see gold always has 79 protons. Many atoms of gold is an element. All right, so this is going to be number 2 in your notes. Pause the video and then continue playing when you are ready. Fill in the blank with the word simpler. Make sure you spell it correctly. Moving on, let's go ahead and talk a little bit about the atomic theory. So all of this you actually already know based on everything we've been talking about through units 1 through 4 and going into unit 5. We know a lot about atoms and elements and compounds already, but you should know that based on what we literally just reviewed. But this actually makes up a big theory of the atom that a scientist, John Dalton, made up many, many years ago. So you can see a good old picture of him over here. Matter is made up of atoms. We already figured out that matter is everything in our universe with mass and volume, and it's made up of small little units called atoms. They're complete units that keep their identity. An atom cannot be destroyed or divided, right? So we can't physically divide it. We can't chemically divide it. Remember, nuclear reactions are a little bit different. When Dalton made this up, he didn't really know about the nucleus yet. So that's a little bit different. But still, the idea is that an atom can't be destroyed or divided without changing its identity. Atoms that make up an element are identical to each other. So again, it's many of the same atoms equals that element. So many gold atoms equals the element gold. Atoms of then different elements, for example, gold versus silver, have unique properties. So gold and silver are very different in terms of how they melt, in terms of their color, in terms of their luster. And so you can see that there are different properties going on. Think about even like oxygen. Oxygen is much, much different from gold. Oxygen's a gas, gold is a solid, okay, at room temperature. Atoms of different elements we then talked about can actually also combine to form compounds. So again, all of this was determined by Dalton before he even actually knew the structure of an atom as we know it today. So he didn't know a lot about atoms, but he was able to make these conclusions, and these have stood the test of time. So this is number 3 in your notes. Go ahead and fill in the blank with unique. Remember, if it's a different element, it has different properties. So fill in the word unique. Make sure you spell it correctly. Pause the video, continue playing when you're ready. Moving on. All right, so before we jump into talking a little bit about what we see about elements on the periodic table, that's one of our objectives, we first want to remember what are protons, neutrons, and electrons in an atom of an element. All right, so remember that protons, all right, if you want, go ahead, pause the video and then take a look at this. You should already know this. We've actually done this table together. So pause the video, try to remember what's the charge of each, what's the mass of each, where are they located, and what's their purpose. I'll go ahead and give you a few moments to pause and continue. All right, so let's go ahead and actually go over this together. So taking a look here, protons are going to be positively charged, right? If you think about the prefix pro, like pros and cons, pros are the good ones. So pros are positive. They do have mass, and the reason they have mass is because they are found inside of the nucleus, and our nucleus is the massive part of the atom, meaning the part of the atom where all the mass is. So it's inside the nucleus, and each proton weighs 1 atomic mass unit, 1 AMU. And its purpose is identity. Remember, if we start to change the number of protons, we actually change the identity of the atom. And again, that can't happen chemically, that can't happen physically. The only way we could do that is if we were to do something like a nuclear reaction, like nuclear fusion, nuclear fission. We'll talk about that a little bit differently, but again, those would totally change the identity of the atom. It no longer would be the same atom in here, okay? So neutrons start with the prefix neutra, which is neutral. So they have no charge, they're neutrally charged, and they still have mass. Again, the reason they have mass, they're found inside the nucleus, our massive nucleus. So you remember all your masses in the nucleus. Neutrons are in the nucleus, therefore they have 1 atomic mass unit of mass each. And then their purpose is stability. Remember that these protons, because they're all positively charged and likes repel, these protons actually don't want to be next to each other. So neutrons, what they do, because they're neutrally charged, is they kind of help to buffer that repelling. And between the neutrons and protons, there's what's called that strong force. And the strong force helps to prevent the protons from their natural desire to repel from each other. So neutrons help with stability, keeping our nucleus from falling apart, which is a really good thing because we've learned falling apart nucleuses, that nuclei, that is radioactivity. Electrons are our last one. We should know by process of elimination, those are the negative ones. You could also think electrons, like being struck by electricity, would be bad, a negative experience. Now, electrons are not inside the massive nucleus. They're actually on the outside of the nucleus, and therefore they actually only weigh they almost weigh no mass. They almost weigh 0 atomic mass units. They have what's called negligible mass, meaning in comparison to the amount of mass that the protons and neutrons bring to an atom, which remember is really tiny already, electrons bring basically nothing, even in comparison to that. So electrons have almost no mass, and we don't really care about them when it comes to calculating the atomic mass of an atom, which we'll take a look at a little bit later. And their purpose is for bonding. Remember, electrons, because they're on the outside of the nucleus, they're the ones that can kind of hold hands with other atoms in order to make compounds and bond and create new things, different substances. Okay? So at this point, based on this, we should be able to go ahead and then answer our next 2 questions, which are number 4 and number 5. Today, we're not really looking at electrons. We'll look at electrons more when we get to our bonding unit. For this unit, we care a lot more about the protons and neutrons and what they're contributing to elements. So protons, again, are positive. They weigh 1 AMU, and their purpose is the identity of the atom. If you change it, it's no longer that atom. Neutrons are neutrally charged. They also have a mass of 1 AMU. Be careful about that. Both of these have the same mass. And neutrons are in charge of stability because they are like neutral buffers. So number 4, go ahead and make sure you select all 3 of these. It is multiple select, and if you miss any of them, it will mark you as 0 for the entire question. So make sure you carefully read, carefully check off these 3. Positive 1 AMU identity for number 4, and then do the same thing for number 5. Pause the video and then continue playing when you're ready. Moving on. All right, so elements on the periodic table have a name, a symbol, an atomic number, and a weighted atomic mass, which is closest to the mass of the most common isotope. So taking a look over here, what we can see, drawing. All right, you can see the name right here. So this one, for example, is oxygen. That one's pretty easy to figure out. The symbol is going to be the letters that represent it. It's usually 1 or 2 letters, so O for oxygen. The atomic number is the one at the top. So this one is the atomic number. And at the bottom, you can see the atomic mass. And remember, the reason the atomic mass is not perfect, a perfect number, is because it's taking into account that there are different isotopes of oxygen. So even though oxygen will always have the same number of protons, remember the number of neutrons can change. And because neutrons have mass, atomic mass can change. But this number will be the closest to the most common isotope. So this is what we can see just from looking at the periodic table. And this actually means we can come to a lot of really important conclusions about about oxygen just by looking at the periodic table. It's an amazing tool. So taking a look here, what is the symbol for oxygen? This should be pretty easy. The symbol for oxygen is O. Again, we just looked at that. The atomic number is the number at the top. Also, it's usually the one that is a whole number. All right, so if you're ever confused, it's whatever's the smaller number and the whole number. So the atomic number is 8. Okay, now the atomic number also tells you the number of protons, which in this case means there are 8 protons in oxygen. And remember, if the number of protons were to ever change, it would no longer be oxygen. So if the atomic number changes, the number of protons changes, then so does the identity. This is extremely important, okay? The protons must always be 8 for it to be oxygen. They're gonna stay the same. Now, atomic mass, on the other hand, is going to be that weird number at the bottom, okay? It's going to be the much larger number because it actually is taking into account more than just the mass of protons. Atomic number is only the protons. Atomic mass takes into account more than that, and we'll talk about that in a moment. So atomic mass is much larger number, and usually it's kind of a funky number because it's the weighted atomic mass, the weighted average. We learned about that a few lessons ago, so if you need to review that, go back to that video, okay? So atomic mass, it's going to be, this weighted atomic mass, again, is closest to the most common isotope. So taking a look here, 15.99999, if you imagine that this is saying like 59, this is actually much closer to the number 60. So we would actually round up, all right? Obviously, we're not rounding up to 60, we're rounding up to 6, right? So this is actually really close to the atomic mass 16. So 15.99999 is really close to 16, so we would actually round up. If it was, for example, 15.11111 or 15.22222, you would round down to 15. But what this tells us is the most common isotope's mass is going to be 16. So in this case, we rounded from 15.999. And we rounded up. So remember, if it's a number bigger than 5, if it's a number after that's 5, 6, 7, 8, or 9, you round up. If it's below 5, so 1, 2, 3, 4, you round down. Okay, so I can write that note here because you will need to know this for your exit ticket. So round up if the number after is 5 through 9, 5 to 9. Round down if the number after is 1 through 4. Sorry, 1 to 4. Cool. All right, so taking a look at this, we already know a bunch of things about this. Sorry, let me move this. I'll move this right here. Cool. All right, so taking a look here, we already know, again, that there are 8 protons for oxygen, and now we know that the mass of it is 16, and it's going to actually be 16 AMUs, right? So 16 AMUs. Now, this is important because, remember, protons are not the only thing that give mass. We just talked about on our last slide that neutrons also give mass. So we can actually calculate the number of neutrons just by knowing the atomic mass and knowing the atomic number, okay? So the number of neutrons is actually going to be the overall atomic mass of our most common isotope, all right, which in this case is 16 AMUs. We're actually going to get rid of the number of protons, so we're going to subtract the number of protons. So taking a look here, I would put in 16 AMUs, and I would actually subtract the number of protons, which is 8 protons. All right, and then if you were to plug this into a calculator or do some mental math, you would know that 16 minus 8 gives us 8 neutrons. So if you take a look here, then you can actually see that the most common isotope of oxygen has 8 protons and 8 neutrons in the nucleus. Again, all of those adding up together to give us a mass of 16 AMUs, and we're ignoring electrons one more time because electrons actually don't have mass. So even though they look really big here, we're going to ignore them when we're talking about mass. All right, if any of this is confusing, make sure that you go back to unit number 4 and you redo the video on atomic number and mass. All right, so this is number 6 in your notes. Fill in the blank with the word periodic. Make sure you spell it correctly. Pause the video and then continue playing when you're ready. Moving on. All right, so where on the periodic table is oxygen? Again, this is super important that you begin to become familiar with the periodic table. That's going to be to Monday's lesson as well. But the periodic table is extremely important because it has so much important information on it, and we don't even need to, like, there's not even that much, but we can figure out a lot about atoms on here. Remember, it has the symbol, the name, the atomic number, which is the same as the number of protons, right? Number of protons, also the identity, and the atomic mass, which is going to be the number of protons plus the number of neutrons. So we can actually calculate the number of neutrons by just subtracting away the number of protons from that atomic mass. So taking a look here, you can actually see oxygen right here. Again, all that information we just broke down is right there for us. It has an atomic number of 8 protons. It has an atomic mass of almost 16, so the most common isotope has 16 AMUs. Take away the 8 protons, and I know that the rest of that mass is made up of 8 neutrons. All right, so make sure that you're really clear on that because you'll need to be able to do that for today's exit ticket, just as a kind of a hint and a heads up. All right, so which of the following are true about nuclear fusion? We already learned about fusion in our last lesson for Unit 4. So again, if you missed that, make sure you go back and review that because all of that information is building together as we go through the quarter. So if you're missing something, you're going to feel very lost later on in the quarter. So make sure that you're really paying attention to every lesson to build it up together. So which of the following are true about nuclear fusion? When you hear the word fusion, you should think of fusing together. All right, so taking a look here, go ahead, pause the video and try to figure out which of these are correct. So there's going to be more than one answer. So 2 nuclei combine to form a heavier nucleus. A heavy unstable nucleus is split into 2 lighter nuclei. It occurs mainly in stars where there's high temps and pressures. This is a safer reaction that produces enormous energy, but it's hard to do on Earth. Or this is an easy reaction to do, but creates radioactive waste and can be dangerous. Go ahead, pause the video, think about that, and then continue playing when you think you have the right answer. All right, so taking a look here, when you think about fusion, again, you think about fusing together. So the easiest one to get here is that it is when the first one is going to be that 2 light nuclei combine to form a heavier nucleus, right? That should be really obvious because that's what the word fusing means. They come together. All right, so 2 light nuclei, like 2 hydrogens, come together to form something bigger like helium. All right, now obviously this next one isn't going to make sense then. This is actually nuclear fission, which is fizzing apart, where we take something and we fizz it apart into things that are smaller, but that's the opposite, so that's clearly not our answer. Now, nuclear fusion does actually happen in stars because remember that hydrogens and heliums are already really tiny atoms and they're already extremely stable, so they don't want to do anything different. It's not like they want to come together because they're already really stable the way that they are. So this occurs mainly in stars because you have to have really high enough temperatures and pressures to kind of force those hydrogens together when they don't necessarily want to be together. They don't want to combine into helium because they're, again, already really stable. So right here, this is going to be our next one. And if they occur in stars, that means obviously it's going to be really hard to do on Earth. Remember, this is actually a safer reaction and it produces an enormous amount of energy because it does power our sun, obviously, which is a star. So it's a really safe reaction because, again, hydrogens don't naturally want to form helium, and so if the reaction were to go wrong, it would just stop because they're like, we don't want to do anything anyway, so we're just going to stop. It's extremely safe. However, it's really hard to do on Earth because currently the amount of energy it takes to make this happen is equal to the amount of energy that we get out, and so we end up with like a net of 0 energy. So it's not yet cost effective. Hopefully eventually it will be. Now the one that is easier again is going to be nuclear fission, the fizzing apart one. So this one is not related. So remember, nuclear fission, the fizzing one, happens in our nuclear power plant, so we can do it on Earth. It is an easy reaction. And the reason it's an easier reaction is we take uranium and we make uranium, which is already really close to being unstable. We shoot a neutron in it to make it unstable, and it immediately wants to fall apart. All right, so that's a lot easier for us to do on Earth, but it does create radioactive waste because it's a really big atom that's still splitting into smaller atoms, but those smaller atoms are still really big. And so the really big stuff is going to be radioactive and not good for us, okay? And it can still be dangerous. Remember that since it's an easier reaction to do, if something goes wrong, it can run away from us and create a meltdown because it creates heat and it can create radiation, and so that would be really bad, all right? That's what's happened with things like Chernobyl. Obviously, we can do it safely on Earth if we're very careful about it, but it would be better if we could figure out how to do nuclear fusion. And you can see an example of a fusion reactor down here. Again, not yet cost effective, but a really fun experiment. All right, let's go ahead and Sorry. Oh, yes. Let me go ahead and give you a few moments. Do number 7. Make sure you click off all 3. 2 light nuclei combine. It occurs in stars. It's safer, produces enormous energy, hard to do on Earth. Make sure you do all 3. If you miss a single one or if you click the single wrong one, it will mark number 7 entirely as wrong. Go ahead, take a moment, pause the video, and then continue playing when you're ready. All right, so moving on, again, stars create new elements through fusion. They, again, bring things together. They're hot enough, they have enough pressure to make bigger things, to force them together. So smaller atoms combine to form a bigger atom, and every star is powered by fusion, because remember, fusion creates an enormous amount of energy, even more than the current nuclear fission that we are able to do on Earth. So hydrogens will combine to form helium, which will continue to combine and will start to form carbon, all the way up to iron. Now, our Earth's sun is actually a relatively mild star, right? It's a yellow star. It's of medium temperature, so our sun actually does not have enough pressure or temperature to form anything bigger or denser than iron. So it can form up to iron, but anything more than that, anything that's bigger than that, it cannot do. However, when a star explodes into a supernova, supernovas do have enough pressure and temperature to begin to fuse much larger atoms. So these can fuse things like gold, lead, uranium, xenon, and krypton, and this also explains why these things are a lot less prevalent on Earth, because they're a lot harder for things like during the formation of our solar system, they're a lot harder of things to make. All right. So at this point, you should be able to match these up. Go ahead, pause the video, try this out on your own, and then when you think you have the answer, continue playing. All right, so let's go ahead and go over this. Again, this should be really familiar. We literally just went over this. Fusion in the Earth's sun can form the lighter elements. It can form them up to iron. So hydrogen, helium, carbon, up to iron. In a supernova, though, which is much hotter, much more pressure, those ones can form the even heavier elements like uranium, radon, krypton, etc. Okay, because it's a lot hotter, a lot more pressure. Atomic number, again, is the same as the number of protons in an element, and don't forget, it's also the identity. If the atomic number or the number of protons changes, so does the identity. And then taking a look down here, an element is anything that cannot be broken down into simpler substances, either chemically or physically. So that means things like gold, silver, hydrogen, helium, carbon, neon, phosphorus, all of those. All right, go ahead, pause the video, fill out number 8 in your notes, and continue playing when you're ready. And moving on. All right, so at this point, we talked about the properties of elements, theory of the atom. We talked about the characteristics of an element that we can identify using the periodic table, such as its atomic number, its protons, its atomic mass, and use that to calculate the number of neutrons. And we were able to explain how fusion creates elements. A lot of stuff that we've reviewed, but kind of bringing it all together in this topic of just elements. So now we're going to go ahead and do our exit ticket. Again, if you've been paying attention, you've been working really hard throughout this lesson, you should do really well and you should get 100% on your notes. If you don't get this last question though, please remember that you will get an 80%, assuming that you did everything else correctly, that I gave you all the answers for. All right, so here's your exit ticket. Again, this is going to be related back to your number 6. So if you need to, you can go back to number 6 to use that as notes. So using the periodic table, we're going to calculate the number of neutrons that are in the most common isotope of lead. Again, I am not giving you the answers. You need to be able to do this on your own. I will kind of help you break down what this question is asking though. Again, we're asking for the number of neutrons, and we want it from the most common isotope of lead. All right, the most common isotope of lead, remember, is going to be related to the atomic mass. You're going to round the atomic mass to its closest big whole number. So remember, if it's 1, 2, 3, 4, if the decimal is 1, 2, 3, 4, you round down. If it's 5, 6, 7, 8, 9, you round up. Okay, so here we go. So taking a look here, remember that you can figure out the number of protons by knowing the atomic number. So you need to be able to figure out which of these is the atomic number. Is it the one on the top or the one on the bottom? Again, we learned this when we went over notes number 6. So if you need to, refer back to that. Rewind if you need to, okay? At that point, once you know the number of protons, you're all set up to do the equation for the number of neutrons. So you can plug in the number of protons, that's what you're subtracting. And then the atomic mass, you already know, is going to be whatever the other of these numbers is. So whichever one's the atomic mass, whichever one's the atomic number, the other one's the atomic mass. But again, the atomic mass, you're going to need to figure out which one is the most common isotope. So figure out which one's the most common isotope. So take that number, subtract the number of protons, and that should give you your number of neutrons. And again, if you need help with that, go back to number 6, go back in the video. All right, so you should be able to answer number 9, type in the number. So all you need to do is type in the number of neutrons, no units. So don't put any units. I already know that it's asking for neutrons. All right, so let's go ahead and move on from here. Pause the video, finish that one up, and then continue playing. All right, so at this point, all you need to do is make sure that you're reflecting on how well you understand our objectives for today, talking about elements, the periodic table, talking about fusion, talking about the theory of the atom. So make sure you pause the video, think to yourself, where are you at? And then moving on. All right, and then make sure that you submit your 5A notes. Thanks so much, everyone, and I will see you later.